my computer science students, you guys have already seen me do it this way, and for the math students, you guys have already seen me do it this way about 5 minutes ago, right? But it's nice out. My house has got somewhat depressing lighting, so I'm outside, and we're going to do a lecture on my iPad. And not only that, but I've got a really cool Desmos presentation to do for you guys today. So I think that's a nice touch.
What if it rains?
Oh, it's not gonna rain. It's beautiful out. But if it rains, I'll move. No, actually, I actually have an umbrella above me too. All right. So, are we ready?
Yep.
Can everybody see my iPad screen?
Yep.
Positive.
Yeah. Okay.
Yes.
I'm not allowed to go outside. That's a shame. All right, so let me switch to my iPad screen too, just so I can see it while I'm writing. Okay, so we had been talking about a sort of abstract thing, an extension of doing like tangent lines, right? And we were making this term up, and we called them quadratic approximations. That's not a made-up term, but what I was calling them was tangent parabolas, right? And so I drawn some pictures for you guys, but I thought it might be a little bit more informative to show you a good picture in Desmos. But before we get there, I want to do a little bit of a recap just so that we can all, catch up with what we were doing the other day. So what we said was we're trying to develop a way of determining whether or not something is a maximum, a minimum, or a point of inflection, okay? Or a local minimum, a local maximum, or a point of inflection. Guys, come on, focus. We can all sing happy birthday to Oleg when we're done. That's okay. All right, so we were talking about classification of extrema is what we were saying, right? And so we were saying there were three possible cases. One case is that it's a minimum, one case that it's a maximum, and the third case, which is that it's neither minimum nor maximum, it's a point of inflection. And we hadn't actually really started talking about what the point of inflection was mathematically. I showed you guys an example of one particular point of inflection that was also a critical value, right? And that was the origin on the graph of y is equal to x cubed. Okay, but they're much more interesting than that, right? That's only one example. I wanted to show you some more. But let's recap. So we had said for any function, right? So let me draw a function real quick. So if I've got any function, ooh, wow, the thickness of my font a little bit, right? If we've got any function that looks like this is f of x. We can find the tangent line to that function, right? I've actually got a little tangent line tool here. So we can find the tangent line to that function, let's say at a point right here. Okay, at that point, and we were calling that point a, f of a. And we said that tangent line is given by the equation y equals f of a plus the first derivative of a times x minus a. Okay, this is P1. So this is a generalization for P1 problems, right? So if I replaced f of x with x squared to do this, exactly what I just wrote down here, you would take the derivative of x, or derivative of x squared, you'd plug in the point that you're concerned with, you'd then put it into point gradient form or whatever method you have for finding the equation of the tangent line, but you would end up with this equation, right? This equation is true for all of the cases, not just for one particular function, okay? Everybody clear with that? This is the first thing that we talked about the other day. Guys, Come on, focus.
Yes.
All right. Then we said we can do something a little bit more interesting, which is we can actually draw a parabola there, right? So we could draw a parabola. Let's say it looks like this. Okay, I don't know. It doesn't have to look exactly like that. This is just an example of one. And as long as we make some restrictions, we made the restrictions that we wanted the function to be the same there. So that means we wanted to actually meet up at that point. We wanted the tangent line to be the same there, right? So the blue line is also tangent to the parabola. And we also wanted the second derivative to be the same, right? And so we came up with an equation that was f of a plus f prime of a times x minus a. So it's exactly the same as the tangent line, but we've got this other term here, f double prime of a times x minus a squared, and then we divided it by 2. Okay, so I told you guys you do not need to know how to come up with this equation, but I do want to show you that this works. Okay, it's not just me doing some random theoretical things with you that don't actually work. So what I'm going to do now is I'm going to switch over to Desmos. I think I still have it open. Yeah, I've got it still open. Ignore what you're seeing. Okay, so what I've got here, aside from a bunch of equations, is a graph of this function right up here, right? So if you look at the function, it's x minus 2 all cubed plus 3 minus x minus 2 squared plus x minus 2. Okay, that's that black line that's drawn right there. All right, the black curve. That's a cubic function. And what I've got drawn on top of that is a circle, right? Remember I told you that a lot of this stuff was like, you're only looking at a small region, right? You don't want to look at the whole picture. You only want to look at a small region. So I've got a circle there that's centered on the curve, right? At a particular point on the curve. In this case, it's AF of A, right? And I can move this around. Oops. I can move this around. Hopefully you guys can see the animation. I don't know how laggy it is, but I can move it around all over the place, and I get more and more circles that are centered on the curve. Everybody seeing that?
Yep.
Yes.
Okay.
Yes.
So what we're going to do then? Yes, go ahead.
What are the triple and quadruple primes?
I'll show you. I'll show you. All right, so what we're going to do then is I'm going to start plotting different approximations. So the very first thing that I'm going to plot is a really stupid thing. It's what I'm going to call the zeroth order approximation. That's not actually a real, I mean, it kind of is a real term. It would be understood if you said it, but it's not really something that's ever done, right? So the zeroth order approximation is just going to be the graph of y equals f of a. Or in other words, the graph of y equals the point that that circle is centered on. So that's this right here, okay? So it's not a very interesting thing. It's clearly a terrible approximation to this curve. It doesn't look anything like the curve, right? But it does actually meet up with the curve at that red point, at the point 2.29, 0.567. Everybody see that?
Yep.
So this is our zeroth and our worst approximation. It's a terrible one. All right, so let's move up 1 degree further, right? So instead of doing our zeroth order approximation, let's do our first order approximation, which you guys know as the tangent line, right? And there's the tangent line. It's a blue curve, right? It's a blue line. It's passing through that point. It's the center of the circle. It's touching the curve, and it's tangent to it. They have the same gradient at that point. So this is a little bit better of an approximation. And in fact, I can make it even better if I just move my circle over a little bit. Oops. I messed up. If I move my circle over, you can see I can find places along this curve where it's a really good approximation. So here, where I've just shifted it over, in this region that I've drawn here, which looks like it's from, I don't know, my 2.5-ish to about 3, in that region, it's a really good approximation. All the x and y coordinates are very close on the blue line and on the black curve. Everybody see that and agree?
Yes.
Okay.
Yep.
Yes.
But
Yes.
good. But I can move this over, and I can easily find a place where the line is a terrible approximation. So it's lagging. There we go. So here, the line and the curve are very far apart from each other. There's not really any similarities between the line and the curve. But if I zoom in really far, or I can zoom in far enough, if I zoom in really far, you can see that they're still pretty close. So what that means is I would have to make my circle much, much smaller. So I'd have to decrease this radius, right? Really, really small for it to be a good approximation. Okay. All right. So I'm going to make the circle a little bigger again, about 1.1 radius. And what I'm going to do now is instead of doing a linear approximation or a tangent line, which is what we've been doing this whole year with derivatives, right? All of the P1 stuff was involving finding this line, right? This tangent line. But this is a case where it's like I can move it all over the place. Right. So now what I'm going to do is I'm going to plot what we were talking about the other day in class, which is our tangent parabola. Okay. So the tangent parabola is right here. It's that red curve. And this you can see. Oh, let's recap, right? If I plot the tangent line on top of it too, you can see just how much better this tangent parabola is at approximating this curve in this region, right? It's excellent. It's actually a really, really good approximation. The line is garbage, right? The line is totally garbage, but the parabola is really good. And again, I can move these around, and I can see that the parabola in general is much, much better than the line at approximating the curve, okay? There's still some spots like right here where the parabola, is pretty far off the curve when I get closer and closer to like, I don't know, it looks like minus 0.4-ish, right? So around there, the parabola is really far off, but in general, it's much, much better than the line. Do you guys agree with that?
Yes.
Okay.
Yep.
All right.
Oh.
So yes, what we're gonna ask me?
Is there at any point that your second approximate, like your second order approximation, is equal to your first order approximation? So I mean, like when your second derivative is equal to 0, evaluated at that point.
What are you asking exactly? Sorry.
So basically, when your quadratic approximation is the same as your linear approximation.
Yeah. That is a really, really important observation. And that's going to occur at a very particular spot. We'll talk about it in a second. It's a really good observation. All right, so yeah, so like you're talking about like right here, right? More or less, right there.
Yeah, yeah, because I was looking, it really looks like a line.
That point is going to be a point of inflection. Right, we'll talk about it in a second. All right, but for right now, just the idea is that the parabola is better at approximating the curve than the line. Everybody agree with that? Like it's a better approximation. Now,
Yeah.
of course, this doesn't have to stop at parabolas, right? It could be a cubic. But here's the thing: my function itself is a cubic, right? It's a cubic. By definition, I made it a cubic. So what if I plot my cubic approximation on here? You guys don't have to know how to do a cubic approximation. Well, it turns out that if it's a cubic and I'm modeling it with a cubic approximation, it will be the exact same function back out, right? So here, that green line that I just drew on top of the black line, you can't even tell the difference between the two of them because they're exactly the same, right? My cubic approximation is going to be exactly the same. And so what I want to do with you instead is I want to take off these approximations and I want to do a curve that's not so easy, right? So a cubic is an easy one. Let's do one that's kind of crazy looking. So I've got this crazy looking curve here, okay? And now this will help us see just how powerful this technique is, right? Because this is a curve that, I mean, if you guys can see, it's the very top equation. It's the square root of x times sine of x times cosine of 10 over x plus 1 plus x squared. Okay, it's crazy looking. And if you zoom out, you can actually see it's like really crazy looking.
That's
Right?
so cool, actually.
It's a really weird function, isn't it? It's interesting. I think it's cool, but it's all over the place. And so what I'm going to do is I'm going to plot each of my approximations. So my 0th approximation is my crap one, right? So it's got absolutely nothing to do with the curve, except for the fact that it crosses at that one point. Okay, I've got my tangent line, which in this region is. What did I do? Oh, yeah, sorry. I forgot. We got to change something. And then I've got to turn this into this is the way that I did it. My programming is kind of weird. Sorry. All right, so here we go. This is my tangent line. So in this region, it's actually really, really good. It's really not bad at all. There's only a couple of spots there at the tail end of my circle where it like gets really bad. But of course, I can move it around, and I can really quickly find a place where the tangent line is garbage. Okay, I could go even further. And there's many spots where the tangent line is a bad approximation, right? So anytime you see the curve and the line are getting really far apart from each other, which is like all of these, like at all of these peaks, basically, or near these peaks, then the tangent line stops being a good approximation, okay? But I can keep going, right? So I can do my tangent parabola now, okay? So my tangent parabola is better. It's much, much better. But of course, there are still many spots, like this one, for example, where it's not very good, right? It's still separating away from my black curve by quite a lot, right? And I can keep finding those over and over again. And I can keep going. Yes, go ahead.
How do you find a tangent parabola?
Tangent parabola is what we did on Tuesday in class. That's where we made it so that the functions were the same at a point, the first derivatives were the same at a point, and the second derivatives were also the same at a point.
Okay,
and
okay.
then by comparing that to the coefficients of a regular parabola, we can actually find A, B, and C for, you know, in the equation ax squared plus bx plus c. Right? It's something that we'll probably talk about a little bit more in detail next year, the actual process behind it, but you actually don't have to know how to do it yourself. It's just the interpretation of the process of finding the tangent parabola is gonna give us a really, really nice method. But I wanted to show you exactly what the tangent parabolas were before we start talking about that method. Okay, so we could keep going, and I could extend my range of A here. I could make it like up to 10. So this way you guys can see a little bit more of the craziness. Right, so I could keep going. All right, it looks kind of crazy. So I'm gonna try and find a spot where it's like really bad. That's a spot where it's pretty bad, right? So you can see that right at the center of that circle, it's pretty decent. But all you've got to do to see how bad of an approximation it is just go a little bit outside the circle, and then all of a sudden you're like, this has got absolutely nothing to do with my curve at all, right? And so what we're going to do then, and this is where it's a little bit extra, you don't really need to know this stuff, but I think it's really interesting to see, is we're going to do the exact same process we did on Tuesday, but we're going to do it again. And instead of doing an approximation with a quadratic, we're going to do an approximation with a cubic function, okay? And so if I add on a cubic function, I get something that's slightly better, right? It's a green curve. I don't know if it's shown up for you guys yet. There we go. It's that green curve, right? I'll highlight it so you can see it. And locally in the circle, it's not great, but it's much better than the parabola, right? And so let's shift it back to a place where we can see a little bit more clearly. Let's go to like there. Why not? Yeah, let's do there. So you can see in my circle, it's much, much better than my parabola. Do you guys agree? Again, you don't need to know where those equations come from.
Yes.
Right? But
Yeah.
if I do them, it's much better. And I can go even further, right? I can do a quartic. So a quartic polynomial is even closer, right? So I can shift this all the way around, all over the place. And the quartic is always going to be better than all of the previous ones, right? So here are all of them on top of each other. Well, the best one is the orange one, right? So I'll let this play and I'll talk a little bit, right? So here I've got my continuous play. I don't know if you guys are gonna be able to see the animation.
It lags a lot.
It's really laggy, isn't it? It's really nice and smooth for me. I'll share the link with you guys. I'll share it in the chat so you guys can actually take a look at it.
So you get a higher order approximation, the better your approximation is.
Say again.
As higher order approximations you get, the better your approximation is.
Absolutely. And there's not really a limit to how many you can do. Okay. If you've got what's called a smooth function, which means you don't have any problem points, no places where it jumps to infinity or anything weird like that, you can keep doing more and more approximations and you can get better and better curves. Okay.
So like a continuous function.
Continuous function, and then it's called continuously differentiable, right? We'll talk about this extensively in further maths next year. It's one of the most important things that we talk about next year. Okay, but this is just a little visualizer, right? You don't need to know how to derive any of these things other than the tangent line. You do need to know how to find tangent lines, right? But we've done that quite a bit. Other than finding the tangent lines, you do not need to be able to find any of these other ones. Okay, I just thought that it'd be a nice visualizer. But one of them is going to be really important. Okay, so let's isolate that one.
Sir?
Yes.
This approximation method is used to approximate very weird functions.
Yes.
But what if we have if the function is weird, won't we have problems taking its derivative?
Sometimes, yeah. And if you have problems taking the derivative, then this won't work.
Sir, are you sharing your screen now?
I should be. Can you not see it?
Is it only me?
No, not me neither.
Okay, it may have stopped. Let me take a look. Yeah, it looks like it stopped. I'm resharing it now.
Okay.
Got it? Yep, there we go.
Yep.
Okay, so what I want to focus on now is not all these crazy approximations, but only one in particular, and that's the quadratic one that we were talking about the other day. I didn't just do this for no reason, right? I wanted to talk to you about the quadratic approximation for a very particular reason. And the particular reason is that it tells us a property of a function called concavity, okay? It tells us the concavity of a function. There are two types of concavity, right? There are two types of concavity that we've actually talked about extensively this year. The only thing is that I've called them something else than what they are, right? I've called concave up things smiley face quadratics, and I've called concave down things frowny face quadratics, right? But that's all it means. Concavity tells us whether or not something is, pointing down like this, like a frowny face, or pointing up like a smiley face. So we're going to define, and I'll write this all down on the presentation in a second, but I want to show you a visualization first, right? We're going to define very soon concave up to mean the same thing as smiley face, right? And concave down to mean the same thing as frowny face. Okay? And what they mean, right? What the concavity tells us is whether or not we are in the presence, right, of, well, what it's going to do for us, right? It's going to tell us whether or not we're in the presence of a minimum or a maximum. So I think we had briefly talked yesterday or Tuesday, whenever it was, about how if something is a frowny face, but we know it's an extrema, then there's only one option, right? I'm looking at the picture right now on Desmos. If I've got a frowny face, but I know that my tangent line is horizontal, let's draw the tangent line as well. It's not exactly horizontal. Let me shift it over until I can get it to be horizontal. Okay, well, it's not perfect, right? But it's more or less horizontal. Actually, it's really not. Let's see if I can adjust the scale. I can't get it. I'm gonna stop in a second. I'll just try and type in like 3, 2, 1, 5. There we go. That looks pretty good. So our tangent line is horizontal and our parabola is frowny, which means there's only one possibility. You guys can see it. It's got to be a local maximum. In that circle that I've drawn, that is the maximum of the function. Do you guys agree with that?
Yeah.
Yep.
Yes.
Okay. Huh? What? Sounded like you said lub. Anyway.
Yep.
Okay. And so the same thing is going to be true, but opposite for minimums. So let's go over to this minimum over here, right? As soon as our tangent is horizontal, which I'll type in again, looks like it's at like 2.52. That's too much. 1, 5, too much. 3, too much. 2, too much. 1. Okay, that's good. All right, so at this point, we've got a horizontal tangent line, right? But our parabola is smiley face, which can only mean one thing. It means that we have a minimum. Okay? Do you guys see this?
Yes.
Yes.
Okay.
Yeah.
Now, here's the really, really important thing. The really, really important thing is that we already know, because we've studied quadratics a lot, we already know the thing that determines whether or not a quadratic is smiley or frowny. What is it?
Coefficient of x squared.
The coefficient of x squared, right? So when a quadratic is ax squared plus bx plus c, if a is positive, it's smiley. If a is negative, it's frowny. Well, guess what? The coefficient of x squared in our quadratic is exactly the second derivative of our function. Okay? So
Wasn't it divided by 2?
It's divided by 2, but we only care if it's positive or negative, and so the 2 doesn't actually matter, right? You're right that it's divided by 2, but because we only care about whether it's positive or negative, we're not going to actually use that for right now. All right, so if you were actually doing the approximation, you would need to know that it's divided by 2. But since we're only considering, we're only trying to figure out whether it's a maximum or a minimum, we don't actually care about that 1/2 factor. All right, but the idea is that the coefficient of x squared in our approximation is the second derivative at that point. And so what we've said is that the second derivative being positive tells us that it's smiley face, which means it's got to be a minimum. And if the second derivative is negative, like it is in the case where it was, 1.625? I think that was too much. 623? No, 62? Whatever, 615. There we go. In the case where it's a negative second derivative, here I'll do this. I'll actually plot the value, or I'll plug in the value of the second derivative at that point too. It's a f double prime of a. Okay, there our second derivative is minus 6.09, right, or minus 6.1, and so it's got to be a frowny face, and so it's got to be a maximum. But when we were over here, I can't remember what the value is now. Was it 2 points? I should have written down 2.25. Nope, 2.511. That's what it was. So here, our second derivative is 19.239, which means that our parabola is a smiley face, which means we have to have a minimum. And this is going to develop into what is called our second derivative test. There's one really, really important caveat here, one really important distinction. We said there were 3 ways of classifying extrema. there were minima, maxima, and points of inflection, right? And we said the points of inflection weren't really extrema, right? But they're something that like disguises itself as being extrema, right? Because the first derivative can be negative, right? Sorry, can be zero. What a point of inflection is, it's going to be the point that's neither smiley face nor frowny face, right? So let me show you what I mean by that. If I just move A around, and this is an observation that Fernando gave us, there's a point between it being smiley and it being frowny that it's neither one. And that's going to be exactly the point where it lies right on top of this blue line, right? Sorry, it should be like a little bit over, right? Whatever. Right when it's, I can't get it. Right when it's right on top of the blue line. And when it's right on top of the blue line, it means it's no longer a parabola, right? It's now a line. And so what would the coefficient of x squared have to be if it's not a parabola?
0.
Zero. And so what does that mean? Our coefficient is given by f double prime. So exactly when we have a 0 second derivative, right, we have a point of inflection. Although, and this is where it gets kind of complicated, that's not always the case. All right. But for almost all of the problems that you are going to have in A-level maths, it will be the case. All right. There's a very important case that you guys already know where this would not be true, where the second derivative could be 0, but you don't have a point of inflection. What is that case? Does anybody have any idea?
A linear graph?
A line, right? Lines do not have points of inflection because they're never smiley or frowny, right? There's no points of inflection there, but the second derivative of a line, no matter what the line is always 0, okay? So
is there another case?
There's just an extension called the nth derivative test, which I'll write it down, but I'm not that concerned with us learning it. We really just need to know the second derivative test. So we've done a lot of the visual stuff. I'm glad I got to show that to you, but we have to actually write some things down as well, right? So we've got to actually formalize all these results. So I'm going to write down the second derivative test in my live board session, okay? Okay, so can everybody see this?
Yep.
Okay.
Yep.
So this is our equation. The blue equation is the equation for our tangent line. The red equation is the equation for our tangent parabola, right? Remember, that's a made-up term by me. Okay, and we said that this tells us that because the coefficient of x squared in this is f double prime of a over 2, it tells us that this is going to determine if the function is smiley or frowny, right? So this tells us smiley or frowny. These are very advanced mathematical terms, not of or frowny. Okay, so let's formalize this a little bit more. I don't know why my font is like defaulted to thick. I'm like on the lowest possible font. I don't want the highlighter. I want pencil. Oh, there we go. All right, so let's formalize this. So we had our first derivative test, which is what we developed on Tuesday, right? So we said our first derivative test was the following. Our first derivative test was that a function f of x, we'll say, has stationary values or critical values, sometimes called critical or stationary points, exactly when, so at the points where f prime of x is equal to 0, okay? So the solutions to f prime of x equaling 0 are called our stationary values, all right? And we said we can classify those stationary values into one of 3 things, right? So we can say the stationary values are either maximas or maximum, a minimum, or a point of inflection, all right? And the way that we determined which of these they were in the first derivative test was by creating a derivative table, right? So That's again kind of a made-up term. But we basically said, let's create a table. Here we've got our x values. Here we've got our f prime of x values, and we're going to plot like our different critical values. So like x1, x2, so on and so forth, right? And then here we're going to say this is when x is less than x1. Here's where it's between x1 and x2. I always make these tables too small, right? And this is where x is like greater than x2, so on and so forth. And we put the signs, SIGN, of the derivatives here. So like we could have like a positive, 0 is going to be for all the critical values. We could have like, negative here, and then let's say we have another negative here. And the way that we classified maximums, right, was by going up, 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 and then going down, 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 right? So we said when we have a plus 0 minus case, this was a maximum, right? And the opposite was true for minima, right? So if we were going down, 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 and then going up, 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 that gave us a minimum. And then the case for points of inflection was where it's going up, 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 then it goes to 0, but then it continues to go up, 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 up again, right? Or the same thing in the opposite direction, right? So it's going down, 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 down. It goes to 0, but then continues to go down, 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 down. All right. But this is not telling us the whole truth. There are points of inflection that don't satisfy that, right? These are only going to tell us the critical values or stationary values that are also points of inflection. But a point of inflection, all it means is that it's neither smiley nor frowny. Okay. So that doesn't have to be a place where the tangent line is 0. That could be something like, let me get a Desmos real quick. So that could be something like right here where I've drawn, right? So the circle is right sitting at basically a point of inflection. This is not a point where it's the tangent line is not horizontal here, right? You can see that in the picture. The tangent line is very much not horizontal, but this is a point of inflection because at this particular point, it's neither smiley face nor frowny face, right? And that's what a point of inflection is. So the first derivative test is extremely limited. It only tells us very particular places where we can find a maximum or a minimum, and we've got to do it by trial and error, kind of, right? We just plug in values and see if it works. So the second derivative test is much more useful, especially when we have, functions whose derivatives we know how to calculate easily. So the second derivative test tells us the following. So the second derivative test, first of all, what you have to do is you have to find the critical values, right? So you need to first find critical values. Right? By solving the equation f prime of x equals 0. So this is exactly the same as the first derivative test, right? The beginning is the same. You've got to first find out where the tangent line is even horizontal to begin with, because you know that maxima and minima, extrema, the plural, right, only occur at places where the tangent line is horizontal, right? That's a given. We've known that for a while. So we've got to start out by at least finding those spots, and then we can classify them. So we can classify them by taking the second derivative. And the second derivative is really simple. You just take the derivative of the first derivative. All right, so in this case, I'm going to use prime notation. So we're going to say f double prime of x. Okay, and let's say for the sake of this, this description, that our critical values are called x1, x2, x3, so on and so forth. Okay, so our critical values are called x1, x2, x3, so on and so forth. Okay, and we're going to try and classify each one of these critical values using the second derivative. And so we'll say if the second derivative, right, if the second derivative of any one of these, right, so I'll put like an xi, this represents any of them, if the second derivative is greater than 0, then it tells us that that shape, the shape of f of x, is what at that point?
It's a happy face.
Yeah, it's a smiley, right? This tells us that it's smiley, or if you want the more formal math term, this means it's concave up.
So it's a minimum.
And so this has to be a minimum. So x1, f of x1, or xi, f of xi is a minimum. Okay, it's counterintuitive because usually you associate like positive with like big and negative with small, but here positive means a minimum, right? And negative is going to mean a maximum, right? Was somebody about to ask something? Sounded like somebody was about to ask something. Anyway, if our second derivative is negative, then this is not a smiley anymore. It's a frowny. Right? And if it's a frowny, the math term for that is concave down. And it implies that this has got to be a maximum value.
And for us to know that it's a point of inflection, the second derivative has to be 0, right?
Yes. Now, there's a little bit of a problem here. I'll show you what it is. I'll write it down, and then I'll tell you guys that you won't probably have to worry about this for this entire course, like AS and A2. But I want to say it just so it's out there, right? So if the second derivative is equal to 0, okay, then typically this is a point of inflection, right? It's typically a point of inflection, but it could also not be a point of inflection. So the way that you test to see if it's a point of inflection is by saying if there is some future derivative, so like the third, fourth, or fifth, or sixth, or something else bigger than the second derivative that's not 0, then it's a point of inflection. But we're just going to say this is a point of inflection. I'll say x1, f of x1 is probably a point of inflection, or is probably a point of inflection. Okay, so remember that there's an exception to this. There are many exceptions to this. Like if I've got the graph f of x is equal to 1, right? That's a horizontal line. There's definitely no points of inflection because it doesn't even make sense to talk about points of inflection if there isn't any concavity. It's never smiley nor frowny, right? So how could there be a point of inflection? There are none. But the first derivative of f of x is equal to 1 is 0. The second derivative is equal to 0. The third derivative is equal to 0. The fourth derivative is equal to, all derivatives are equal to 0. So in this case, the second derivative is equal to 0, but there's no point of inflection there, right? So we've got to be a little careful there. Like I said, I have my serious doubts that this will ever come up on an Edexcel issued exam. In some curriculums, it's crucial that you know it, but for us, it's not the end all be all, right? We don't have to know this case. We do need to know what a point of inflection is, but we are just going to say in Edexcel, I'll say in Edexcel, in Edexcel, we can pretty safely assume that any solution to the equation f double prime of x equals 0 is a point of inflection.
Sir?
Yes, go ahead.
What about if it's not a concave up, concave down, or a point of inflection?
Well, those are the only three possibilities, right? Because concave up is uniquely defined as being a place where the second derivative is positive. Concave down is uniquely defined as being a place where the second derivative is negative, and neither is where it's neither positive or negative. The only other possibility is that it's equal to 0, right?
Okay, and why then is probably a point of inflection and why not definitely?
Well, because of the example that I gave, right? When you've got a constant function, okay, there's no concavity to begin with, right? It's neither concave up nor concave down to begin with. So, but if you take the second derivative, you will get 0. So you get 0 as your second derivative, but it's not of a point of inflection because there's no concave up or concave down.
Yeah.
So there can't be a place between the two of them, right? That's just the case where the entire function vanishes. It's not just at a single point. It vanishes everywhere. Same thing goes for a line, right? A straight line is y equals mx plus c. Take the first derivative, you get m. Take the second derivative, you get 0. The second derivative of a line is always equal to 0, but there's no points of inflection on a line. Does that make sense?
Yes, sorry, sir. My internet is crap.
That's okay. That's okay. Yeah, just wanted to make sure that you heard me. Okay. So this is the second derivative test, and it's immensely powerful. It's immensely powerful. For the purposes of Edexcel maths, we have just solved every maximum and minimum problem that we want to. So let's do an example, a worked example, where we can actually apply this test. All right. So let's write down a random. Let me actually, I'll pull up Desmos. Let's open up some random one. See if they give us a cubic default one. It doesn't look like they do. I'll just do a new one. All right, so let's come up with a decent looking function. Y equals, let's do a cubic. X to the power of 3. I want to give it some stretches, some maximums and minimums, so we'll go like x squared plus x. No, that's not good. I want it to have some stretches, so maybe let's do like 2. Yeah, there we go. That looks pretty decent. And maybe we can shift it over a little bit. No, that's fine. We'll leave it like that. So let's try and find analytically, right, by hand, not using Desmos, although Desmos looks like we could probably do pretty quickly. Let's try and find the coordinates of this maximum, right, that point right there, which is like minus 1.33333. And then, of course, it looks like the origin is another point where it's a maximum. But let's do it by hand, and let's do the classification of it using the second derivative test to show us, to give ourselves some idea that this is actually working. All right. So our graph was, what was it? X cubed plus 2x squared. Okay. So we've got y equals x cubed plus 2x squared. So we're trying to find and classify using calculus. This is what they usually say in exams, right? Using calculus. All the extrema. So this means the minimums and maximums, I should say local extrema, right? Local means in that circle. So let's go back to our page where we talked about the second derivative test and see what steps we have to actually follow here. So the first thing it said for us to do was find the critical values, right? By solving the equation f prime of x equals 0. So let's do that. That's a really easy thing to do for this problem. And then after that, we're going to classify what those critical values are, right? Well, we're first going to take the second derivative, but we'll get there. So what is the first derivative? Well, the first derivative, change colors for our solution. Our first derivative is just dy dx, right? What is dy dx? Somebody tell me the derivative here.
3x
3x squared plus 4x.
I asked for that, I guess. So we hit 3x squared plus 4x, right? Everybody agree?
Yes.
All right. And what do we have to do with this derivative?
Find its root, so make it equal to 0 and find its.
Perfect. We're going to set it equal to 0 and we're going to solve. How do we solve this equation?
Quadratic formula.
Take out the x.
Quadratic formula? Are you joking me? We're not using the quadratic formula here. We're going to take out the x. I think Oleg, you suggested that.
No.
So we take out. It wasn't you?
If in doubt, just
He's
take the
joking.
quadratic formula.
Whatever, Khalid. So we're not in doubt. So we'll
Sir, I'm just being you. You always say that.
That's true. You've got me there. But this is an easy enough one where we don't need to do the quadratic formula, right? So we're going to pull out an x, and we have two possibilities, right? What are the two possibilities?
X is equal to 0, and x is equal to -4/3.
Right. We have x is equal to 0, or we have 3x plus 4 is equal to 0, which gives us a solution, right? X is equal to -4/3. All right. So these are our critical values, right? Our critical values are, they're occurring at the origin and -4/3. There's no coincidence that -1.33333 is the decimal equivalent of -4/3, right? And our other point is the origin. So that part at least is working. But now we've got to classify them. And the way that we classify them, so I'll circle them to make sure we know that these are the critical values, right? These are the critical values. Let's say crit val. Okay, we've got to classify them by taking the second derivative. So the second derivative, the notation is a little bit weird. So when we're using Leibniz notation, you typically do d squared y over dx squared. How that originated, I actually cannot tell you. I have no idea where that comes from, why they put like the 2 in between the d and the y on the top and the 2 after the x
I
on the bottom.
do.
Where does that come from? Do you know?
Because it's first d over dx of dy over dx.
Mm-hmm. Yeah, so I guess, yeah, it tells you that you're doing two operations of d over dx. Yeah, I guess that makes sense. Yeah. I don't know who first came up with it, though. I don't know if Leibniz himself did that notation or if it's something that just happened over the years. Anyway, it doesn't matter. But this is the way we write the second derivative. All right. And what is the second derivative? Well, just take the derivative again. So what is the derivative of that equation there?
6x
X.
plus 4.
6x plus 4. All right. And so here's what we're going to do. We have to figure out, is the second derivative negative or positive at each one of these critical values? So we're going to plug in our critical values. We're going to plug in crit val. Right? So let's plug in 0. When x is equal to 0, what is d squared y dx squared equal to?
4.
4, right? That's easy enough. Is this positive or negative?
Positive.
Probably positive.
I hope that's not a difficult one to answer, right? So we got positive number. And we'll analyze this in a second. We'll determine what that means. But let's plug in x is equal to minus 4/3. What happens if we plug in
Minus
x is equal to... Say it again?
Minus 4.
We get minus 4 when we plug that into the second derivative. Do we?
Do we?
We get minus 4. Yeah, we do. Is minus 4 positive or negative? Well, yeah. I don't know why I'm asking that question. That's a negative number. And so what we've just determined, remember what we just determined, is that when x is equal to 0, we have a horizontal tangent line, right? That's what this was. This tells us there's a horizontal tangent line there. And this has just told us that the parabola is smiley face. So if we have a horizontal tangent, but it's smiley face, what type of extrema is this?
It's maximum.
Minimum. Smiley.
Minimum. It's the opposite of what you think, right?
Oh, sorry, sir. I thought you meant for the minus 4.
No. This one. So this tells us that this occurs. This is a minimum, right? Which tells us that the point 0, 0, right? That's what you get when you plug it into y, is a minimum, right? Does that make sense?
Yes.
And same thing over here. We now have said that by taking the second derivative, we've got a negative number, which means it's a frowny face. So if we've got a horizontal tangent line and a frowny face, what type of extrema does it have to be?
Max.
It's got to be a maximum, right? And so we'd say that the point minus 4/3, and then what do you get when you plug that in? I guess I can just go to Desmos. 1.185. This has got to be a max point. All right. And of course, we can do this with much more complicated equations. I chose an easy one that we could all understand really easily and find the derivative really easily. But this technique is going to be useful for all sorts of different things. We already did earlier on in the year when we were only using our first derivative test, we already did problems where we found like the maximum possible volume for a box made out of a sheet of metal, let's say, for example. Well, now we can prove using the second derivative test much more easily that we've actually found a maximum or minimum to those problems, right? So we'll do more of those. Next time we meet, we'll do some examples of some harder problems where we have to find our own equations based on the actual, a problem that's described to us, and we'll work through some of those, and we'll do this. I don't want to rush it too much, but we do have to go into our last unit on integration fairly soon. Okay. So we'll do probably 1.5 more sessions of this. If we need to, I can do one of my own videos like I was doing earlier on in the quarantine. We'll cross that bridge when we come to it. Okay. Hopefully, yes. Go ahead.
Sorry. So tomorrow we're having our P1 exam, and then next week for maths, are we having an M1 exam, right?
I would like to. We have to discuss that further.
Okay,
but
because
like
we haven't finished P2.
No, we haven't finished P2. We're close to it, but we haven't
So
finished it
P2 is going to be like next week.
Yes, probably.
Okay.
Right. All right, guys. That's it for right now.
Sir,
yes.
the thing is, having two maths and further maths exams per week, at least for me, it's a lot.
Fernando, I don't know what you want me to do. I can't push back the date. It's not my date. I don't know what I don't know. I don't have any other options. I
For
know that
me-
it's a lot, but that's all we
Everyone
have.
has a lot of exams. It's not up to the school, it's up to the exam board.
Yeah, for me it's
Exactly.
also a lot, but I feel like once we get over done and over with everything, it's gonna be easier. So
But when is the deadline?
We don't really know yet. They haven't released it yet, but we're assuming that it's going to be around the same time as Cambridge, which is the end of May. We'll
And
we'll
why
see.
are we gonna have 4 exams in a week if we only have 3 left to do?
We haven't said anything about doing 4 exams in a week. We haven't said that.
Okay.
All right, guys. I'm sorry to cut you off, but I've got an exam right now, so I need to make sure that I get to it on time. I've scheduled a post, so it shouldn't be a problem, but the post scheduler has been kind of unreliable, so I need to go check it. Okay.
Okay. Bye.
Okay,
right.
bye, sir.
Bye, guys.
Bye, sir.